Okay, so yes, apologies that the assignments are still not published. We are proofreading them, checking them that everything's fine, and I'll publish them. I'll probably publish physics today and maths soon after. So yes, I need to share my screen. So today we are talking about differential equations in physics. And here is the draft assignment. It's pretty much ready, so you can start doing problems from it. So I'll send the link in the chat. So you can look at it. So we'll be looking at radioactive decay, water discharging from a container, then dragged and terminal velocity, the rocket equation, and some oscillations. Okay, so the oscillations is the hardest part, the most interesting perhaps. Okay, so have you done differential equations in school or otherwise? Yes or no? Have you done differential equations? Please reply in the chat. Okay. All right, you look at them, but don't in school. So you get it more or less, you understand what they are. A differential equation is an equation which contains derivatives, and the aim is to find a function that fits effectively. Okay, so if you say the derivative of y is equal to y, for example, yes, it's a very simple differential equation, and the solution would be y is equal to e to the power x is a solution. Okay. Right. How do we know that it is a solution? Well, we can solve this differential equation. So the solution. So we write dy on dx is y. We separate the variables, so we multiply both sides by dx and divide by y. So we get dy divided by y equals to x. Then we integrate both sides to get dx. We integrate both sides. The integral of dy over y is logarithm y equals x plus c, and then y is e to the power x plus c, which can be written as e to the power x multiplied by e to the power c, and we just let e to the power c equal to c dash, and that's equal to c dash multiplied by ex, where c dash is a constant. C dash is a constant. Right, so that's how you solve it. Okay, I hope that makes sense. So of course, this is one of the solutions. One of the solutions. So there are multiple solutions. So y equals c multiplied by ex is the all solutions. So any solution in the form is valid. Okay. And differential equations can take different forms. So for example, the second derivative plus y equals 0. This is what we call a second order differential equation because it has the second derivative. We'll be looking at this equation further on. Second order differential equation, etc. So I hope you get you have an understanding what differential equations are. So what we're trying to do. Another example of a differential equation is uniformly accelerated motion. Uniform accelerated motion. In this case, we have acceleration is equal to a constant value. So let's call it, well, you know what? Acceleration is the rate of change in velocity, dt, is equal to a, which is a constant. Now, if we write dv equals a dt, and we integrate both sides, we get v equals at plus c. Let's call it c1. And if you let t equal 0, then v is equal to c1. Therefore, c1 is the initial velocity. So we have v equals at plus the initial velocity, which is u. So we get a very familiar equation, u plus at. So this is also a solution to this differential equation. This is a differential equation, and this is the solution. But this is also a differential equation because v is the derivative of the displacement. Dx dt is equal to u plus at. And we can separate the variables here as well. Dx is equal to u plus at dt. And we can integrate that. And we get x is equal to ut plus at squared over 2 plus c, where c is the initial position. We usually write the initial position as x0. So we have x equals x0 plus ut plus 1/2 at squared. And you can write further, x minus x0 equals ut plus 1/2 at squared, and this is s equals ut plus 1/2 at squared. So this is also a solution to the same differential equation, right? Okay. So I hope that makes sense. So let's look at some particular differential cases. I've done webinars on this topic before, so you can always watch them. Let's look at problem 2. A hot cup of coffee initially at 80 degrees cools down, and after 10 minutes, the temperature is 50 degrees. The temperature in the room is 20 degrees. Find the temperature as a function of time. So you have a hot cup of coffee, and the temperature is T, which depends on time. So T is a function of time. And then the temperature outside is 20 degrees. Let's call it temperature of the room. And T0 is the initial temperature is 80 degrees. 80 degrees. Right. So we need the Newton's law of cooling. Newton's law of cooling, which says that the rate of energy transfer, the rate of heat transfer from the cup, heat dt, is proportional to the change in temperature, to delta T. In other words, dq dt is equal to a constant, let's call it alpha multiplied by delta T. Now, the thing is this value is negative. dq dt is negative. dq dt is less than 0 because as the heat is given away, it's decreasing. Therefore, it's minus. Okay. And we certainly can say that Q is, well, Q is the amount of heat is definitely proportional to, well, Q is Cm delta T, for example. Yes, so you can imagine that this is proportional to dt over dt. So in other words, we can write that dt over dt is equal to minus, we need a new constant, let's call it k delta t. So the rate of decrease of temperature is proportional to the temperature difference. And we can write that as dt over dt equals minus k multiplied by temperature of the coffee minus the temperature in the room. And now we can separate the variables. So dt divided by t minus tr equals minus k dt. Now we integrate both sides. Now, there are two different approaches when you're doing differential equations. I'll show you both. And I'll show you both. So the first approach is using indefinite integrals and using definite integrals. I personally prefer using definite integrals, but I'll show you both approaches. Am I saying it correct? Definite, indefinite integral. Yes, of course. Using indefinite integrals. Where you take the integral and you have a constant. So you have the integral of the left-hand side is going to be the logarithm of t minus tr equals minus kt plus c. Because the temperature of the coffee will always be greater than the temperature in the room, so we can drop the logarithm, the modulus, and then we can say that t minus tr is equal to, you know what? A very good practice is instead of c, you use log c. Because, well, you'll see why. Is going to be e to the power minus kt plus logarithm of c, which is equal to c multiplied by e minus kt. It just looks prettier. It doesn't matter if you write c or ln c, like it's the same thing. because C is just an arbitrary constant. And then you can say the temperature is the temperature in the room plus yes, plus C multiplied by E minus KT. Okay. Um, to find C, well, first of all, we want to find C. Okay. When T is 0, we know that the temperature is 80 degrees, and that means 80 equals temperature in the room plus C multiplied by e to the power 0. And that means C is equal to 80 minus 20, which is 60 degrees, which is 60. So C is 60. And now we want to find K. To find K, we substitute T equals 10 minutes. And the temperature is 50 degrees. So 50 equals temperature in the room, 20, plus 60 multiplied by e to the power minus kt. And here we have k times 10, 10k. So we have 30, 1/2 e to the power minus k times 10 equals 1/2 minus k times 10 equals logarithm 1/2. K is equal to logarithm 2 divided by 10, which is 0.06, I'm guessing. Logarithm 2 divided by 10. 0.0693. Okay, so that gives you the value. So temperature is temperature in the room, so that's 20 plus 60 e to the power minus 0.0693 times t. And that's your answer. And let's draw that. Desmos. Y is equal to 20 plus 60 e to the power minus 0.0693 x. And yeah, you just can make it a little bit fancier, x greater than 0. And that looks very reasonable because you could imagine that the temperature of the coffee indeed changes according to this law. You can see that initially the temperature is 80. Then after 10 minutes is 50 degrees. And then after a very long time, After about 60 minutes, it's 20 degrees, which is perfectly reasonable. Okay, does that make sense to you? Do you understand everything? Okay, cool. The second approach, so up to here, like I personally find C, using C, a little bit awkward. So I don't like using the constant integration because it doesn't always, yeah, like do you use lin C or C? It's not always easy. So I prefer using a definite integral. In this case, I rewrite the integral, but I change the limits. I apply the limits of integration. So I know that the time starts at 0 and finishes at T, and the temperature starts at 80 and finishes at T. Well, T is the final temperature or the current temperature. And then my integration becomes slightly easier because now I have a logarithm of T minus TR between limits AT and T, and equals minus KT between limits 0 and T. So here I can go logarithm of 80 minus 20, because temperature of the room, minus logarithm T minus 20. And that's equal to minus KT plus 0. Okay, so that's just here. Now here I have logarithm of 60 minus logarithm of T minus 20. What am I doing? Sorry. Of course, it's plus and minus. Apologies. It's that minus that. So I did it the other way around. This logarithm T minus 20 divided by 60 equals minus KT. And here T minus 20 over 60 is equal to e to the power minus KT. And then I get T minus 20 equals 60, e minus KT. T equals 20 plus 60, e minus KT. I get the same answer, but I personally find it less awkward when I have the limits and not and yeah. Which one do you like? Which one do you prefer? The first method or the second? Or you can have no preference. It's fine. Indefinite. Okay. Second seems neat. Okay. 50-50. Right. And then you do the same. You sub 10 to get 50. Sub 10 t equals 10 and t equals 50 to get the final solution. Problem 3. A skydiver of mass 60 kilograms has terminal velocity of 50 meters a second. Assuming air resistance is proportional to speed, find the speed as a function of time. Okay. So first we start by drawing the skydiver and the forces acting on the skydiver. So the forces are mg and the air resistance. And the air resistance is proportional to the speed. So it's kV. Okay, and write Newton's second law. Mass times acceleration is mg minus kv. Okay. Now, to find k, So at terminal velocity, acceleration is 0. And that means mg must equal to kv. And therefore, k is equal to mg divided by terminal velocity terminal. So that's 50 meters, well, 60 kilograms times 10, g is 10 for simplicity, divided by the terminal velocity, which is 50. Okay, so 600 divided by 50. Is it 12? 12. Yes. Sorry, that's embarrassing. 12. Now the unit. The unit mg has a unit of newtons and terminal velocity. So newtons divided by terminal velocity, meters per second. But that is Newton is kilogram meter per second. Meter second. So, ding, ding. So it's 12 kilogram per second. Okay, that's the coefficient of air resistance, if you wish. In the assignments, it doesn't matter if you use 9.8 or 10. Yeah. You can argue either way. I if you want to get used, you don't want to get used to 10 because you have your A levels on one hand. On the other hand, like assuming AG is 10 is no big deal. For compos. Okay, so you went okay. That's nice. So we have the value. So we will use that later on. Okay, so m dv dt is equal to mg minus kv. And now we can separate the variables. We can do m dv divided by mg minus kv equals dt. Okay, so what I did, I hope you can see that. I divided by mg minus kv multiplied by dt. Now I integrate that. And I'm going to use my second method, which I prefer. Oh, actually, oh yeah. Okay, so velocity changes from 0 to v, and time changes from 0 to t. Okay. So this integral m goes out, and this is minus kv. So this integral, I really hope you can see that, is the integral of 1 over ax plus b. It's this integral. So it's 1 over a logarithm ax plus b. Let's see. So this integral. So it's m divided by minus k logarithm mg minus kv, right? Between limits 0 and v. And mg will be greater than kv, right? Because kv starts with 0 and it increases up to mg. So this would be a positive value, and that's equal to t. So we can write ln, you don't need the modulus, mg minus kv equals minus kt divided by m. And we have mg minus kv equals E minus kt over m, and v is equal to mg over k minus, have I missed something? No, I don't think so. I'm inconsistent with the units. Sorry, something's off. Why am I getting these values? Of course, yes. Apologies. That's a good exercise in self-correction. So I've noticed a mistake. Do you understand how this is a mistake? Sorry. Um, the lin should be divided first. No, it's not about the lin. I was mistaken with my limits. So how did I notice the mistake? I noticed the mistake here because this value has no units, because this is a unitless quantity, and e to the power this is unitless. Unitless. And these have units. They clearly have units of newtons. Newtons and newtons. That means this equation is invalid. It's wrong. So that's how I know that I've made a mistake. And the mistake is this. When I substitute the top limit and then I subtract, and I have to substitute the bottom limit, and it's not zero. It's minus, so yeah, I was in a hurry doing that. So t, it's minus m over k, and it's plus m over k logarithm mg. Right. So then I multiply everything by k, so I get ln mg minus kv plus minus logarithm mg equals minus kt over m. I'm going this way. So logarithm mg minus kv divided by mg is equal to minus kt over m. So these are all positive values, so that's fine. I can get rid of the modulus, and then I get mg minus kv divided by mg is equal to E minus kt over m. Now this is a unitless quantity, this is a unitless quantity. So now I multiply it by mg, so I have kv is equal to mg minus mg multiplied by E minus kt over m. So V is mg over k, open bracket, 1 minus E minus kt over m. Brilliant. So now I just need to sub in the values. So V of t, m is 60, 600 divided by k, which is 120, open bracket, so 12, 600 divided by 12, open bracket, 1 minus E minus k is 12, and m is 60, so 1/5 to 0.2 t. So that's 550 multiplied by 1 minus E minus 0.2 t. All right, let's sketch that. Y is equal to 50, open brackets, 1 minus E to the power minus 0.2 x. And so we can say x is a positive value. Beautiful. And you've probably seen this graph before. Probably seen this graph before. So we can see that the velocity, so this is the velocity of the skydiver, and this is the time in seconds. So it takes the skydiver approximately 30 seconds to reach terminal velocity, which is a reasonable thing. All right. Okay. And now we're getting into the wonderful second order differential equations. Now, I'll show you some approaches of solving. Okay. So to solve a second order differential equation, have you done second order differential equations? And oh, have you done second order differential equations? No. Okay. All right. So you're hopefully you're in for a treat. So we're looking at function. So what is y if the second derivative of y plus 5 times the first derivative of y plus 6 times y is 0? Okay. It does look like a quadratic equation. And to solve it, we will be using a quadratic equation. So what we do is we say, well, let's search for a solution. Let's search for a solution in the form y equals a e lambda x. Okay. And then we find the first derivative. So if y is a e lambda x, where a and lambda are unknown constants, we find this first derivative, And the first derivative is going to be A lambda E lambda x using the chain rule. And the second derivative is going to be A lambda squared E lambda x. Right, does that make sense so far? And now we sub that in and we get A lambda squared E lambda x plus 5 A lambda E lambda x plus 6A E lambda x equals 0. We just sub these values into the equation. And we can see that E lambda x cancels and A cancels. And we get a quadratic equation, lambda squared plus 5 lambda plus 6. Right. So the solution, this is called a characteristic equation. Characteristic equation. And if you have a characteristic equation, or also known as an auxiliary equation, then we can solve it. Of course, we know that lambda 1 is equal to -2, and lambda 2 is -3. Is it? Yeah, -2 and -3. And therefore, y would be equal to a multiplied by e minus 2x plus b times e minus 3x, where a and b are constants. Because we found the solution, like this one, this is the solution. So this is the solution that both of them are solutions. Okay? And then you can find A and B by applying the initial conditions found from initial conditions. And that's it. That's what makes differential equations of the second order super easy. So all you need to do is write down the characteristic equation and then write down the solution. So y is equal to a e lambda 1x plus b e lambda 2x. And that's it. Okay. However, the quadratic equation doesn't always have a solution. Oh, by the way, yeah, the shape of this solution, well, it's an exponential curve, right? It's an exponential curve. However, if you look at the second equation, well, you write down the characteristic equation, lambda squared plus 10 lambda plus 25 equals 0. Then you have lambda equals -5. And here, this is a slight trick. So the solution y of x is going to be ax plus b multiplied by e minus 5x. Right? Because we can't have two constants with the same e values. All right, so it's repeat roots basically. Because the discriminant is 0, it's repeat roots. All right. And finally, the most interesting case is this. Here, the characteristic equation plus 4 lambda plus 13. As you can see, the discriminant is negative. So I'm going to complete the square. Plus 4 plus 9 equals 0. So lambda plus 2 squared equals minus 9. So lambda plus 2 is equal to plus or minus root of minus 9, which is 3i, plus or minus 3i. So lambda is minus 2 plus or minus 3i. Okay. So I'm going to write down the equation in the same format. It's going to be y of x is equal to a multiplied by e to the power minus 2 plus or minus 3i x plus b e to the power minus 2 plus, oh, what am I doing? Plus 3ix minus 3ix. I can take out e to the power minus 2x, and I'm left with a e to the power 3ix plus b e minus 3ix. Okay. I don't want my solution to have imaginary numbers. So I'm going to do some tricks. First of all, I recall Euler's formula. That e to the power ix is cos x plus I sine x. And therefore, E3ix can be written as cos 3x plus I sine 3x. And E minus 3ix can be written as cos minus 3x plus I sine minus 3x. We know that cos is an even function, therefore we can just remove the minus, cos 3x. And sine is an odd function, so we take the minus out, sine 3x. And we can sub that in. So therefore, y of x becomes e minus 2x, open bracket, a cos 3x plus ai sine 3x plus b cos 3x plus o minus bi sine 3x. Now let's combine them. E minus 2x, a plus b cos 3x plus a minus b I sine 3x. Let C is equal to a plus b and S be a minus b times I. And therefore, y of x equals E minus 2x multiplied by C cos 3x plus S sine 3x. Ta-da! So that brings us to the rules for second order differential equations. If you have y ay double dash plus by dash plus y equals 0, this is called a homogeneous second order differential equation. You have if b squared minus 4ac is greater than 0, then you have y of x is equal to a e lambda 1x plus b e lambda 2x. So where lambda is the two roots. If b squared minus 4ac is equal to 0, then y of x is ax plus b e lambda x. And if b squared minus 4ac is less than 0, then y of x, then lambda is, let's call it p plus or minus I omega, plus or minus IQ. Let's keep it simple, plus or minus IQ equals e to the power px, open bracket, a cos qx plus b sine qx. All right, that's it. Does that do? How well do you think you understand these solutions on a scale of 0 to 10? Any particular questions or clarification which you would like to? Which you'd like? It's quite a straightforward method. Okay. The equation of simple harmonic motion. So simple harmonic motion. So let's try to apply this to physics. So let's say we have a mass on a spring, and the spring constant is k, the mass is m, and this is the origin. So if we displace the mass by x to the right, then it experiences a force, and the force is minus kx. So F equals minus kx. That's the force acting on the mass. Force is mass times acceleration. And acceleration is the second derivative of x. So mx double dot is equal to minus kx. So we can write mx double dot plus kx equals 0. Interesting. So this is a differential equation, right? And as you can see, A is, well, comparing it to ax double dot plus bx dot plus c x equals 0, you can see that A is m, b is 0, and c is k. A squared, or b squared b squared minus 4ac is negative. Therefore, you have the third option. Okay. So the characteristic equation. So I'm going to rewrite this as x double dot plus k over m x equals 0. So the characteristic equation, lambda squared plus k over m equals 0. So lambda is equal to plus or minus square root of k of minus km, so I. I'm going to use a substitution. Let omega equals square root of k over m. Therefore, lambda is plus or minus omega I. All right, so now I have my solution. X of t is equal to a multiplied by, well, yeah, let's do it. Let's do it a uh, cos ae minus omega t, omega I omega t plus b e plus minus I omega t. And let's do the whole thing again. So a cos omega t plus b sine I b sine omega t plus a I sine plus b cos omega t plus b minus b I sine omega t, and I sub let c is a plus b, and s is equal to a plus minus b times I, and I get x of t is equal to c times cos omega t plus s sine omega t. And that's the solution. But you already know that, well, this could be written as r multiplied by sine omega t plus phi, right? You've probably studied that at A level. If not, we can leave the answer like this. Now, suppose suppose if we pull and release, yes, if initial position of mass is x equals a, then you can sub t equals 0. T equals 0, so x of 0. So that's equal to c multiplied by 1 plus s multiplied by 0. And that's equal to a. Therefore, c is equal to a. Now, we also need to find the velocity of t. So we differentiate that. So we get c omega sine omega t plus s omega cos omega t. And we know that the velocity is 0 initially. And when we substitute the initial velocity, we get, sorry, it's a bit hectic here. V of t is equal to minus c I've just differentiated x omega of 0 is equal to 0 plus s multiplied by omega times 1, and that's equal to 0. Therefore, s equals to 0. So x of t is equal to cos, so it's going to be a cos omega t, an equation that you are familiar with, I'm sure, right? A cos omega t, that's the equation of simple harmonic motion. We've just shown that. So hopefully that makes sense. Now we're getting to really, really interesting territory. The damped oscillator. A damped oscillator is where you have an oscillating system, but there is a resistance to the motion. Right. So let's say the mass is displaced from the original position. So that's the equilibrium position, and that's the displacement x. And it is moving in that direction, v. And it experiences two forces. So first of all, it experiences a force minus kx. That's from the spring. And it also experiences a force of gamma v minus gamma v. Okay, right. So we can write that mass times acceleration is equal to minus kx minus gamma v. Gamma is coefficient of, well, it's not coefficient of friction. It's a coefficient of proportional. It's resistance. Okay, let it be water resistance or air resistance, right? So some sort of resistance. And then we have m plus gamma x dot and plus sorry, let it not be gamma. I'm going to use gamma later on. Let it be bv bv plus kx, and that must equal to 0. And to simplify things, I'm going to write x double dot is equal to x double dot plus b over m x dot plus k over m x equals to 0. I'm going to let omega 0 equals to k over m. Omega 0 squared is k over m. And I'm going to say that gamma is equal to b over m, just for convenience, because I don't want to carry fractions with me. And therefore I get x double dot plus gamma x dot plus omega squared, omega 0 squared, and that's equal to 0. The characteristic equation for this looks like this: lambda squared plus gamma lambda plus omega 0 squared. And we have three cases, right? So we have b squared, so gamma squared minus 4 omega 0 squared. So if that is positive, that means the solution, well, the solution would look like this. X is e to the power minus kt plus b e minus mt. So something like that. So the solution would look like, would if this would be an exponential curve. Exponential curve. If gamma squared minus 4 omega 0 squared is equal to 0, that would be an exponential curve of maximum steepness, which is called overdamping. There's a mistake here. Overdamping. So critical damping. Critical damping. Critical damping. And if gamma squared minus 4 omega 0 squared is less than 0, then you have underdamping. That's where you have sines and cosines. So in case of critical damping and overdamping, you have no repeated motion. So you can think of it like a pendulum in very thick oil, like a pendulum underwater, right? Take a pendulum, put it underwater, it just goes wick and stops. So no repeated motion. If you have a pendulum in honey, it will take a very long time. It will just stop. And if you have a pendulum in air, it will go boom, 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 boom until it dies down. Right? So exponential curve. So that's you imagine a pendulum. Example. Pendulum in honey. Example, pendulum in water. And underdamping is pendulum in air. So depending on the amount of damping, depending on the amount of friction, you have very different behavior of the oscillating system. It can go like this. Yes, it can go shook and stop, or it can go very, very slowly and stop. Okay. And these are the types of damping that you study in school. You just don't do it as a quadratic equation. All right. So now if you solve this, so I'm more interested in the underdamping. The most interesting case, suppose gamma squared minus 4 omega 0 squared is less than 0. And then the solution x of t is going to be e well, okay, we need to solve the quadratic. So lambda is equal to minus gamma plus or minus square root of gamma squared minus 4 omega 0 squared. Okay. And divided by 2. So that's minus gamma over 2 plus or minus, well, you can write it as gamma over 2 squared minus omega 0 squared. And then you can write down the solution. Is going to be E minus gamma over 2, open bracket, A cos square root of gamma squared over 2 minus omega 0 squared times T plus B multiplied by sine square root of gamma over 2 squared minus omega 0 squared. T. Well, this is negative, of course. So it would be the other way around, right? Because we've taken out the negative. So it would be plus minus plus like this, right? I hope that makes sense. And then, so suppose we let go from the furthermost position. So we swing it and let go. Suppose at t equals 0, x is maximum. Let x is a, right? So I should have used c and s. X is a is the amplitude. So we release it from the furthermost position, and that means x of t is going to be equal to e minus gamma over 2 multiplied by a cos square root of gamma over square root of omega 0 squared minus gamma over 2 squared times t. Right. If you draw this graph, you can see that this is a cosine curve. This is the frequency. This is the angular frequency. So because the system has damping, the frequency would be slightly less than omega 0. Omega 0 is the frequency with no damping. And omega 0 squared. So omega 0 squared minus gamma over 2 squared is less than omega 0. So this is the new frequency. So do you understand that if you have damping, you would go slightly slower, right? Make sense? And let's just call it omega. A is the initial position, is the initial amplitude, and this term, this is the amplitude. Amplitude, and the amplitude is decreasing. It's exponentially decreasing. So there's t, of course. It's exponentially decreasing with time. So the graph would look like this. So we start with the maximum displacement, x, and as time goes by, so if we draw an exponential curve like this, so this line is e to the power minus gamma over 2t. Let's play around with some graphs. So y equals e to the power minus 0.2t. Too steep, 0.002. 0.002. No, too small. multiplied by 40, 60, multiplied by cos 0.2t. That's too small. 0.2t return 0. Could you ask? Probably not. I think it's too complicated for an admission interview. They would be more interested in more basic stuff. Maybe this 0.1, 0.5 cos t. Oh, beautiful. This is a damped oscillator. This is a damped oscillator. Okay. Now, the difference yeah. So the new frequency is that. So you have the final solution, the equation of motion is x of t is equal to a multiplied by e minus gamma over 2t times cos omega t, where omega is the new omega. All right, so that's the equation of a damped oscillator. Now the next part is forced oscillations. That's even more complicated, but yeah. Let's look at this equation. So the difference is that on the right-hand side, it's not zero. So to solve this, you need to do it in two stages. Stage one, just make it zero. So first, solve the homogeneous equation. Okay, so homogeneous equation looks like this: y double dash plus 2y dash plus y equals 0. So you just make it 0. And then you solve it. So lambda squared plus 2 lambda plus 1 equals 0. Lambda equals -1. So y, we call it y0, right? And it's going to be a x plus b multiplied by e minus x. That's the solution to the homogeneous equation where it's 0. In the second part, we find the particular integral. So this is called the complementary function. And then find the particular integral. Find the particular integral. Right, find the particular integral, and the particular integral is a function the particular integral is a function in this form. So what I mean by particular integral? particular integral is, in this particular case, is lambda cos 2x plus mu sine 2x. The particular integral is one of the solutions to that equation, and you obtain it by substituting this value. So we search for a particular integral in this form, where lambda and mu are to be found. And then I do, so if this is y, then y dash, the first derivative, is going to be minus 2 lambda sine 2x plus 2 mu cos 2x. The second derivative is minus 4 lambda cos 2x minus 4 mu cos sine 2x. And when we sub that into the original equation, so we have minus 4 lambda cos 2x minus 4 mu sine 2x plus minus 4 lambda sine 2x plus 4 mu cos 2x plus lambda cos 2x plus mu sine 2x equals 25 cos 2x. And to find lambda and mu, we just equate the left and the right hand side. So we combine the like terms. So these have to be equal, and these have to be equal. In other words, minus 4 lambda plus 4 mu plus lambda must equal to 25, and minus 4 mu minus 4 lambda plus mu is equal to 0. Solving these simultaneously, we obtain so 4 mu minus 3 lambda is 25, and 4 lambda is minus 3 mu. And how can we do that? So mu is 4/3. Mu is minus 4. Lambda is minus 4/3 mu. No, lambda is minus 3/4 of mu. So 4 mu plus 3 multiplied by 3/4 mu equals 25. So 25 mu divided by 4 equals 25. So mu equals 4. Okay, and lambda is minus 3. Lovely. Okay, I just solve these simultaneously, and finally, I get my particular integral. So the particular integral, I prefer to call it y1, particular integral, is equal to minus 3 cos 2x plus 4 sine 2x. And now I have my final solution. Solution is always the complementary function plus the particular integral. So we found the complementary function. So y is equal to y0 plus y1, which is ax plus b multiplied by e minus x. plus minus 3 cos 2x plus 4 sine 2x. And where does this come into play? Well, this comes into play where you have forced oscillations. Forced oscillations in where you have an external force pushing the system. So for example, you can think of a child on a swing and you're pushing the child. So that's an external force. And the external force is this. So you have the oscillating system, and that's your external force. So let's look at it in a real life scenario. So here it is. The total force acting on the system is the friction plus the force of the spring plus the external force, external periodic force. So that's external, no, driving force. All right. Now, we don't torture you. We don't ask you to actually solve this differential equation. The one that I just did. Okay, so we won't ask you to do that in maths, but not here. But this is the solution. We give you the solution. And then we just ask you to verify that this solution is actually a solution. So one of the questions in the assignment is to differentiate that twice and verify that 16 is a solution of 14. So what you do is you just substitute that into here and see if it works. Okay. Okay, we have one question remaining, but yeah. Okay, well, let's. Unfortunately, I don't have enough time to do it. But it's done the same way. It's just afterwards you substitute the initial conditions. So you solve it the same way, then you substitute the initial conditions to find A and B. Use this to find A and B. I will talk more about this in 2 weeks because the maths assignment is incredibly similar to physics. So we'll do more equations in maths. Right, I hope this was useful. And so I'll see you in 2 weeks' time.